landing on Budapest, Hungary on Sunday, 14 August 2016. At midday on the 15th of August, they went to the lake to study the place. On the evening of that same day, they brought all their material outside the hotel, which was about 100 meters away from the lake. So they used the distance between the hotel and the lake to calibrate the collimator lens for the powerful laser they brought. And here is Dave Moore trying to explain how they were doing it.
So it looks like we're calibrating the laser, bouncing it off of a mirror way over there, just to see if the collimator is working. We're getting a nice coherent beam. Can't need that, otherwise we'll end up with a beam over 10 miles that spreads out to about a mile wide. So this is our laser expert. And what she's doing is trying to adjust the collimator using the reflection from the mirror that's way over there.
Now they are getting ready for the leveling process and positioning the laser that is going to be at 50 centimeters above water surface.
Not fully horizontal level, but 89.998 degrees, so it's like 1 or 2 thousandths of a degree, which is sloping downwards actually if it's a globe. So, let's start it. Feljelölni. Hol van rajta az 50 cent, és akkor nem kellene méreget. Just put it onto that.
Figyelj csak, Sanyi. Nem lenne az jobb megoldás, ha...
Gumipókkal csak így lefogatjuk, mert nem fogunk gyorsan menni. Megnézzük be talán. És itt igazából a lényeg az, hogy gyorsan jelöljünk, mert megy a nap.
Előrefele gyorsan megy, akkor nem mond, akkor semmi baj nem lesz csak.
Hátrafele meg biztos nem megyünk, de előre sem megyünk gyorsan.
Here they are measuring and marking a point that is exactly as 50 centimeters above water surface to make it visible and easier to measure.
Egy hosszabb vonalat, és a másik oldalra ad ide, másik oldalra húzza.
All the way to the other end, so that
this pen isn't going to be good enough.
Nem fog rá.
nem, mert vizes. Úgyhogy akkor simán jelöljük.
De várjál, van nálam egy érzet.
Megfossa azt, hogy hagyjad már.
Hagyjuk, ragasztjuk végig, az legalább jó vastag.
De hát az se ragad rá a vizes.
Akkor nem fog lejönni, hogyha most ráragasztunk.
Az nem biztos, hogy annyi már, hogy a vége elég.
Hát ez a legfontosabb vonal, aztán a többit meg majd meglátjuk. Ez az 50 centi.
Ja, van ilyenetek, ezt kell hozni.
Here's our laser expert plugging in the laser and trying to line it up. We've got a spirit level on there, so I'll level up the spirit, level up the laser.
Steve Torrance, please explain what happened the first day.
In one of the first tests around 6 a.m., the laser was set up at an altitude of 50 centimeters. During this test, there was some interesting effect with the laser beam. With the boat at around 1,500 meters, the beam went from 50 centimeters high to almost 2 meters in what appeared to be a short distance. From various pictures examined after the test, we could see that the beam was reaching the other shore, but in one particular picture it showed a sharp uprising of the beam that seemed to indicate that refraction was causing the beam to rise up.
Maybe you can photo this. I can do this, so you know how high it is.
This was during the leveling process before the level was established. Laser was pointed down 0.016 degrees. Here are some pictures that show the sharp uprising of the beam from the Canon 650D and also from the Nikon P900. After modeling it in 3D, it was determined that the laser was pointed slightly down at an angle of 0.016, causing it to contact the water surface at about 1,500 meters, and then rising at the same angle, contacting a building on the other shore 8 kilometers away. It appears to hit that building at about 2 to 3 meters high. The reason for the apparent sharp rise in the laser, shown in the camera on shore, was just due to its high degree of zoom. The Canon 650D had a focal length of 1200 millimeters, which caused the reflected part of the beam to appear shorter and rise quicker. In this animation, you can see the effect of the zoom lens going from 6 millimeters to 1200 millimeters and how it gives the illusion of the far reflected beam rising up quicker and being shorter. It is just an optical illusion of the zoom lens.
So this is the second day of the experiments. This time our crew decided to put the laser at 1.25 meters, which is 4.1 foot above water surface. So before we show you the experiments, let us explain to you what's been done in the second day, and then we're going to calculate everything in AutoCAD and let you compare the numbers with the last experiment's results.
To make sure we had the laser leveled according to the Globe Earth model, we did a slope correction on the laser. The curvature drop at 720 meters would be 0.04 meters, so we added this to the 1.25 meter laser height to get a perfectly horizontal line of the laser according to the Globe Earth model. Since our laser was at a slope-corrected height of 1.29 meters, and we aimed the beam to 1.32 meters, we had a 0.0023 degrees upward bend according to the Global Earth model. So how does this leveling affect either model? Well, with the flat Earth water surface model, it results in the laser having a 0.005 degree upwards angle, resulting in the laser beam having a slight rise in height over distance. On the Global Earth curved water surface model, it results in a 0.002 upwards angle. So let's see the test results.
Okay, so here is the flat Earth and the Globe Earth. I placed them close to each other so you can see them better. I'm gonna zoom out so you can see what I'm doing. So this is the Globe Earth, and this table on the right side shows the real measurements. I want you to watch the calculations on this video and compare them to the real measurements on this table, okay? Now let me show you the height of the laser, and as you can see it's at 1.25 meters, and if it was leveled then at 720 meters it should be at 1.29 meters, but it was pointed to 1.32 meters because it was pretty difficult to put it at 1.29 meters, okay? And by the way, the white line represents a level line and the green line represents the laser, okay? So if we move to 870 meters, the laser on the Globe Earth should raise up to 1.34 meters. Now you can just focus on the green line and the green number and forget about the white line, okay? So let's move to 1800 meters and the laser should raise up to 1.58 meters. And let's see how high the laser is gonna be at 6,000 meters. It should be at 4.32 meters, okay? That's what we should see if the Earth was a globe. Now we're gonna see the calculations on the flat Earth, but take a look at the table again, okay? So here is the laser. I put it at 1.25 meters, and I only drew one line here, which is the green line that represents the laser. Now we're gonna go to 720 meters to show you that the laser was set at 1.32 meters. Please notice that the laser here is pointing upwards too, okay? Now we're gonna move to 870 meters and the laser should be at 1.33 meters. Now we're gonna go to 1800 meters and the laser should be at 1.43 meters. Look at the table again, please. Now we're gonna move to 6,000 meters, and if the Earth was flat, only if the Earth was flat, the laser should be at 1.84 meters. Our team couldn't get the exact measurements here, but on the video,
That's hitting me right now. I got it.
We've got the beam right in our faces here.
you can see the beam hitting the camera, and the camera was at 1.79 meters. So the difference is only 5 centimeters only. The divergence of the beam could be more than that. I will let you make your own conclusions.
So let's see what happened. At 720 meters, the laser was leveled to 1.32 meters. At the next stop at 870 meters, the globe Earth and flat Earth measured 1.34. A couple stops later at 1800 meters, the globe Earth would have marked 1.58, instead was 1.42. At 2,670 meters, it would have been 1.92 meters on a globe. And at 3,716 meters, it marked 1.58 meters, and on the globe it would have marked 2.48. At 3,890 meters, it marked 1.6 meters. On the globe it would have marked 2.6. Then another 10 measurements were taken until the final measurement at 6 kilometers. In the globe Earth model, that would have resulted in a laser height of 4.32 meters. Instead, what was recorded was 1.79 meters, confirming the surface was flat.
Here's our team getting ready for the last measurement. The laser is at 1.25 meters, 4.1 feet above the water level. First, we had to make an initial leveling of the laser beam at position C1 near the shore. We then went to the next leveling position to fine-tune the laser beam height. At these leveling distances, we are fine-tuning the laser beam angle in arc-seconds increments. Let's listen to some of our conversations.
Can you measure it there?
You got a tape measure?
They measured the height of the laser beam and told us to angle the beam upwards more. The laser beam angle was adjusted in very small increments. This procedure was then repeated at position C1, C2 and C3 with the final leveling position at C4. You can see that the laser beam always had the same diameter on the board, an indication that our laser beam divergence was very minimal. The new collimator lenses made just for these long-range experiments was performing very well. The laser beam was perfectly collimated with a minimal divergence
Then we
at
should
long
set it a little
distance.
bit up.
90 centimeters.
Okay, then we move a bit up.
Finally, the laser beam at C1 was near the black tape that indicated 1.25 meters from the water level, so we continued to test the next position. Now the boat has reached position C2 at a distance of 436 meters from the laser on the shore. As you can see, the laser is pointing slightly downwards here, so that we adjusted the beam upwards slightly. As we move further away from the shore, the laser level will require even finer adjustments to set the level accurately. It is important that the laser is leveled at the 0.005 degree of accuracy for the long-range measurements.
It's too low. It's still too low.
Yep, we see it, so we're gonna raise it a little bit.
Accurately leveling the laser is only possible by using the boat in the leveling process.
Just a little down. That's just a little down a little further.
We made a fine-tuning of the laser beam level here at position C2 and recorded the same beam divergence as we had close to the shore. The boat floated slowly to keep the beam on the board to the next position C3 at 631 meters from the shore.
Okay, that would have been perfect.
No, it would have been a bit too much.
Okay,
that's okay.
That's perfect.
Ez jó, tökéletes, azt mondja.
We confirm here that the laser beam at position C3 is at the accurate height level. We had to aim the beam a bit upwards to slope correct for the amount of curvature drop on the globe Earth curved water surface model. The water was very calm, so our measurements were accurate to a very high precision. At a distance of some kilometers, the wave height of a few centimeters, like an inch, is negligible to our measurement values. We can now conclude that the accuracy of the laser measurement is very precise and will give a conclusive result on the curvature experiment.
Okay, that's close enough.
Okay, then I put the phone down and just call me when something happens.
Okay, right.
Okay, cool. Ciao.
Now the boat starts to float to the leveling position C4 at a distance of 720 meters from the shore. Here is a video from the boat with the Nikon P900 camera at Niku's eye level. As his feet are at the waterline in the rubber boat, we know we have the exact camera lens height matching his body eye height. Here you can see Canon 650D video 1 meter above the water level on the shore at position A. Our captain is trying to keep the beam on the whiteboard so we can make the continuous measurements with the cameras.
We're gonna remeasure it or lower it?
Well, no, because I've already measured the distances where that tape is, so
Okay.
we're pretty much good.
So we gotta keep it at that distance.
Yeah.
It's gotta stay there.
So
how far are we right now?
We evaluated the distances after the experiment based on the GPS coordinates from the Samsung phone that records GPS and timestamp with each pictures. The measurement points were evaluated on the laser height and the beam divergence at each measurement position so as to get the most accurate reading from the laser height over the entire distance.
okay, so let's go.
Can we check the timestamp on the
Sorry?
picture? Let's check the picture.
They checked the camera to make sure that the time and GPS stamp was being recorded on the pictures. We used this method of filming and taking photos of the laser beam on the board to make the measurements as quick and accurate as possible. Let's fast forward our boat ride to the next measurement positions. Our captain keeps the boat in line with the laser beam so we could make a lot of measurement readings at the different distances. As the boat moved further away from the original starting position, the boat became less and less visible to the naked eye, as well as to the teleobjective camera located at position A. We were lucky to have a huge cloud blocking the sunshine on the lake so that we could record measurements until 7:30. After that, the sun was too bright to see the laser beam at such a long distance. The air temperature was 17 degrees Celsius, 62 Fahrenheit, and the lake temperature was at 22 degrees Celsius, 72 Fahrenheit at the time of the measurements. This means that the direction of any possible refraction would point upwards, but we did not experience any noticeable refraction of the laser beam. Now, it's time to see the experiment results.
Let's go. So, hold on. Ready? Go. What's the word for go?
Go?
Go.
The boat is now far out at over 3 kilometers 1.8 miles away. The boat is on track with the laser beam as it goes further out, and we also can see a laser beam directed at around 4 kilometers 2.5 miles here. As the clouds disappeared and the late summer sun was shining strong, the laser became more difficult to detect. After they found the laser beam, they proceeded to the next measurement point. The beam height was always at horizontal distance from them and never up above their eye height. The boat is now over 5 kilometers 3.1 miles distance from the shore, and we start to see the bottom of the boat disappearing. This is the NUTS, non-uniform density transition zone over the waterline that is blocking our view of far distant objects like our boat and the buildings on the opposite shore or the bottom of the skyscrapers in the teleobjective skyline photos. Our laser beam was high enough to avoid the non-uniform density transition zone. Now the boat is over 6 kilometers away, sinking into the NUTS, the non-uniform density transition zone. Soon after we lost sight of the boat.
Hello? Hello, is the laser still on? Yeah. Is the laser still on?
Yes, it is.
Yeah, we're having difficulty finding it. Because we can't see the beam anymore, we can't find it.
Yeah, it's because we have sunlight.
Yeah, but we'd still, we were still seeing the direct beam, but we just can't find it anymore. So we're about 1 kilometre from the other side.
Okay, so it's like kilometers.
Yeah, be about 9 then.
Then about that, we have the laser beam outside. And then direct kilometers.
Okay. Okay then. All right. Hold on. Yep. Okay. All right. We'll head back now, but we'll keep looking for the beam. Yeah.
Okay.
Okay. We'll do.
I film most of the way this way. Should I take photos?
Yeah.
If I see the
So
beam?
did you say film on like shots of the other side? Okay. Yeah.
Yeah, I filmed.
Okay, so a couple of shots. Oh, okay. With this shot. Okay, I'll take a couple of shots and we'll go. All right. Bye. We're not far from the other side. So.
Let's put it on speaker so I can hear him.
Oh, okay. How do you? Hang on a second.
If you're fine, do all the recordings that you can because this camera is also off from the battery.
Okay.
And when you're finished, then just drive back.
Right. Yeah.
And then I think this is gonna be perfect. This last scene is gonna be awesome.
Yeah.
Yeah, it's hitting me right now. I got it.
We've got the beam right in our faces here, and it's stayed nice and level. It's not quite on the board anymore, but we've still got it in our face, so it's great.
Just record that you have it on your body and that's awesome.
Okay.
Like that.
All right. So we'll call you when we're on the way back.
Okay, super.
Okay.
Okay, so.
All right. Bye. Excellent.
Yep, it's right in our face.
Yeah,
So.
let me see if get one more picture.
I'm gonna pause the video and I'm gonna take a couple pictures too.
Okay. Oh, there it is. Yep, got it. Right. That's the limit of what we can really see.
I still don't find it.
You've got. You actually got it?
No, I don't find it yet.
Okay, let's find it one more time. Let's find it one more time.
They couldn't see the laser anymore, not because of the curvature of the Earth, but because of sunlight and refraction. It was pretty hard to see the laser from that distance. So that was the end of the experiment. We couldn't talk about all the measurements that have been done in 2 days, but in the description we're gonna leave a link to an Excel sheet with all the necessary data. We were supposed to use a helicopter to film this test, but we couldn't hover above the lake. But we will use it in one of the next experiments. I'm not gonna say anything about this for now, let it be a surprise. If you like what we do, subscribe to my channel Dr. Zach and also Steve Torrance to see a precise model of the universe, and the man's channel, the links are in the description, and here are some videos of the helicopter.
as a being, yeah, are just a collection of memories. Yeah. And that collection of memories defines who you are. If you don't know what's coming next.